Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really interesting hangout planned for you today. We're going to delve deep into some of the technical details of using the Hubble Space Telescope, and specifically how we calibrate the data that come off of the telescope. So with me, as they are each week, are my cohorts and colleagues, Dr. Carol Christian, she's the Hubble Space Telescope outreach astronomer, and Scott Lewis from KnowTheCosmos.com, the Virtual Star Party, and the Internet in general. So welcome, guys.
I will be your guide.
I will be. So welcome, and they are here to help me with this hangout. But before I get started, I want to make a quick announcement that we're going to be getting started this week, and you'll see some more social media postings on it from our channels next week as well. NASA is trying to make trying to get a panel together for South by Southwest. Now that's that's usually held in March, and that is because the Hubble 25th anniversary will be so close by. It'll have a very heavy Hubble component, but to get the panel, I guess South by Southwest is having a voting process. I don't know if they always did this, but this year it's a voting thing, and I've put the link to how to vote in the details of the Google Plus Hangout. I've also been retweeting people who pointed to the links on our Twitter channel as well, Jason Calilbrating, Amber Strawn, those guys. So if you have a moment, please go and vote for the Hubble panel at South by Southwest so that we can get that rolling. We'd very much like to be there and show you some of the latest things going on with Hubble at South by Southwest. So I wanted to make that announcement. As far as this hangout goes, before I get to the introductions of my guests, let me just say, interact with us, folks. And by now, if you've watched with our Hubble Hangouts for any length of time, you know the drill. The Q&A app is my favorite. It's the easiest. It's very cool, very easy, very handsome. I like it. So use the Q&A app. You can also comment on Twitter. Hubble Hangout is the hashtag, and we'll see that as well. And come on, folks, tweet. I mean, we haven't had any Twitter activity on that hashtag since we had Libby Doodle on there. So please, come back.
Hey, Libby Doodle is awesome. And
yeah, she was great.
Yeah.
So please tweet at us using that hashtag as well. As always, there's the comments on YouTube and Google Plus event page as well. So get ready. Tell us your thoughts and your comments and your questions, and we'll get to them later on in the Hangout. So today, we are talking about the Hubble Space Telescope and getting what we do with the data from it. Now, astronomy and cosmology, probably more than any other science, really benefits from the laws of electromagnetic radiation. The laws of physics that govern how a photon gets to us, its wavelength, its place in the universe. All of these things allow astronomers to learn about places we could never hope to get to. They're just too far away. The outer, distant reaches of the universe are accessible to us because of the photons that travel to Earth from all of these different places. So what's really cool about this is that astronomers have developed all kinds of techniques for gathering these photons. And we're talking about some pretty faint photons, folks. I mean, some of them literally arrive in just a few batches of photons at once, and some of them travel for billions of years, and they finally get to the Hubble Space Telescope. Their feeble signal hits the detector, and depending on what the detector is made of, whether it's silicon or mercad telluride, whatever it happens to be, those photons will somehow create using the photoelectric effect, a little electron, and those electrons spread throughout, and we do all kinds of wonderful things with them. We're going to talk about that today. But like I said, astronomy and cosmology, gets to benefit, I think, more than most other sciences about this. And it's also a topic, but none of it actually can get done without calibrating the images that we take, because as these photons are falling onto the detectors, they're building up signal, and images are being created, and they're being transmitted down to the Earth, and we're doing all kinds of stuff with it. And that's the topic of this Hangout. What are we doing? What is the stuff that we're doing to these images once the raw data have been taken, and to not only make the pretty pictures that come out of it, but also to do meaningful science? How do we know about things like the distant universe, the distant galaxies, what the exoplanet atmospheres are made of, whether there's even an exoplanet there or not? So These are things that we're going to talk about today. It's a subject near and dear to my heart because up until the time I started working at the Institute, this was my career. I worked as a person who wrote software to calibrate astronomical images. In fact, I called myself an astronomical programmer, and that had less to do with how good of a programmer I thought I was as to the type of programming I did. So, and for the young people out here watching this hangout, if you're thinking about a career, this is a growth industry. Writing code that calibrates astronomical images is in high demand right now. In fact, if you watched our Pan-Stars hangout with Robert Lupton, he came on and basically begged for programmers to go work for the LSST. So this is a growth industry. So if you're young, just starting out in your career, it's something to think about. And today we're going to talk about some of the steps to do that with. And with me today are 3 astronomers that all work at the Space Telescope Science Institute. I have, and I'm going to go from my left to right, Dr. Dean Hines. He's an astronomer here at the Institute, Dr. Jay Anderson, and Dr. Jennifer Mack. Welcome, guys. You guys are all experts on calibrating data for the Hubble Space Telescope. And I think last week we had a workshop on Hubble calibration. Now, Hubble's been around for almost 25 years. How come we're still meeting to talk about calibration? Jennifer, can you help us with that? Tell us a little bit about the workshop.
Okay, well, so I think really the main point of this was to tell people how to get the most out of their data. So they get calibrated data products that are in our archive, and what we're trying to let them know is what are possibly some limitations in those data products, how well calibrated are the different instruments, and what can they do at their home institution to maybe reprocess those and make them even better. And so when we talk about calibration, you had talked about, we measure some electron, so that's actually what we get. We'll get a raw image with some number of counts, and then what the goal is of calibration is to translate that into some sort of an absolute brightness. So imagine, you had a 60-watt bulb and you were and you put it a mile away, and you could measure, oh, I got 10 electrons from that, and then you can tie that. You can tie that to an absolute system. So what we do is we look at stars that we know how bright they are on in an absolute sense, and then that's how we can tie everything to sort of an absolute brightness.
Okay, so do astronomers meet every year? Do we have this workshop every year to talk about these problems and issues with calibrating, or is this just a once in a while we do this?
Every few years we get together.
Every few years?
For this, yes.
Okay. Well, great. So let's go back.
2005, 2009, or 2010, 2014.
And I imagine there's somebody has figured out some cool way of doing something different, and maybe it's a good way to learn about these kinds of things with Hubble data. Now, you brought this up, so let's talk about this for a second. Hubble is sitting up in space. We all know that. It's looking all over the universe. It looks at everything from planets to exoplanets to distant stars, distant galaxies. And the photons come in, they hit our detectors, they get transmitted down to Earth via the system of satellites called TDRS. We get the data at the Institute. What does it look like when we first get it, when we first see it?
So I have a slide there that...
Okay, Scott, can you put that up for us?
It's so pretty.
Okay, so this is an example of a raw image from the Wide Field Camera 3 infrared detector. So you can see there's a galaxy. You can see a lot of other structure in there. For one, you can see the 4 different amplifiers. You can see some kind of striping. So a lot of what you're seeing here is signal from the detector electronics. When you're looking at in the infrared, it sees heat. So it sees heat from the instrument itself, and that actually kind of blinds you a little bit. So what we do is first we remove that signal, and you can flip to the next image, and then you can...
Okay, wait, before you go though, go back one more time. Those 4 big squares, what are they again?
Those are 4 different amplifiers. This
is a raw image from the Wide Field Camera 3. It's in the infrared range because that's the kind of camera it is. And these 4 big squares they're 4 amplifiers. Is this typical of all cameras, or is it just the WIFC-3 that has 4 amplifiers?
So far as the WIFC-3 does, the ACS does. I'm not sure about the others.
And they're
Nick
all at
Moss
different
had
levels,
it.
it looks like, because...
Most detectors on telescopes have at least 4 detectors, amplifiers, if not more.
Okay.
They're not always blocked like this, but they typically have more than one, so you can read out the problem is you have to be able to read out the charge, measure the electrons quickly, and the more amplifiers, the faster you can go.
And you can't make 4 amplifiers that are exactly the same. Is that why they look different? Is that the reason for them being different? They're so distinct.
That's correct.
Okay. So and I'm also seeing some little stripes here, and what do those stripes do to those big thick stripes that are like several dozen pixels wide? Do you see those?
I don't know exactly what that is. But this is all just signal from the detector itself.
Okay, so maybe read out as it was read out or something like that. These artifacts.
So let me just say, okay, sort of like your cell phone, we have these little tiny solid-state detector elements that are in an array, and that's what you're seeing, 4 arrays. And when the charge is accumulated, it's sent to a bit bucket, essentially, and the amplifier then sends it to the rest of the electronics. And so sometimes you have variations between each one of the little pixels, but you can also have variations that are along bands, and it's just how the electronics get read out, and then that's kind of noise. And so what Jennifer's describing is, well, that's not an astronomical image yet, because a lot of the stuff that's coming out is not from the galaxy, it's from the detector. So we want to get rid of that stuff so we can say what's left is exactly from the galaxy and not from the detector. Because even if you try these kind of exposures at night with your cell phone and your friend's cell phone, you'll get different kinds of things that may have those kind of features. It's just that we use our phones when there's a lot of light and we don't see all that stuff. But it's a similar technology.
Excellent, thank you, Kelly. So the takeaway here, what I wanted to show was that the camera, the nature of the camera itself, introduces all these things that have to be dealt with. Now, these are known things. We know how the amplifiers act. We know about how the camera's read out. But this is what it looks like. This is how the camera was built. And there's a lot of other things embedded in there. But I just wanted to point out that these images don't come out looking so great. Okay, go ahead and go.
Tony, one thing to point out to the listeners, though, and the viewers, is that even though this looks like it's bad, these are state-of-the-art detectors. This is the best we can do with technology at the time.
That's right.
So this is good stuff. It's not that these are bad detectors. These are really state-of-the-art.
Oh, that's true. Any astronomy camera on any telescope will have these sorts of things in them, and they cost, like you said, they're state-of-the-art. So
that's right.
It's just the nature of doing CCD astronomy.
Right. In fact, they even cool the detector so that signal is minimized as much as possible. So.
How cold are we? I mean, we're in deep space, obviously. We're in space, not deep space. But how cold are these cameras generally? Do you know?
I think around minus 80 Celsius.
Okay.
Cool. That's about right.
Okay. All right, go ahead. I'm sorry. Now you can go ahead, Jennifer.
Oh, sure. So the next frame just shows once we remove that additional signal, then bam, there's your galaxy.
Boom.
Yeah, you've got all kinds of little tiny background galaxies, little star-forming regions in the galaxy. So
we're not just using an Instagram filter here, right? We're doing a little bit more processing.
We haven't really done any processing besides removing the detector electronics here. So we've got a lot of bad pixels, bad columns, we've got cosmic rays, and you've got a lot of junk in the image that we can get rid of.
So this is an image. This is step one.
We're not using Instagram. No, this is not Instagram.
Right.
It's not Photoshop either. This is
No.
known physical attributes of the detector, and all we're doing is removing them systematically and correctly.
That's right. And the important thing is known systematic errors. These cameras are characterized way before they're launched to figure out how are these amplifiers going to read out. Where are the bad pixels, if any? Where are the bad columns, if any? And we know these are things about the detector itself that we know and can remove, and they don't change much over. Well, do they? Do they change much over time? Those characteristics, Jennifer?
I'll let Jay handle that one because he's the master of.
Oh, okay, Jay.
Pixels.
Jay Anderson.
Yeah, the detectors do change over time. For instance, when cosmic rays hit the detector, they create a defect in the detector. So sometimes a pixel that was good all of a sudden becomes bad, and we either have to flag it or we can correct it. And so that's one of the things that I'll be talking about.
Okay, cool. Excellent. All right. Go ahead, Jennifer.
Okay, so if you just flip to the next frame, it's a little bit hard to see, but in this, what we do is we take many exposures, so you can kind of blink back between those two. It's a little hard to see, but there's just speckled with cosmic rays. There's just high energy particles that are coming at us from the sun, and they just kind of sprinkle the detector.
Yeah, they look like little dots in the image.
Yeah, little bright dots.
Yeah.
So we take multiple exposures, and then the cosmic rays fall on different pixels in each time. So then we just replace those pixels with the other images.
Okay, so how do you know those are cosmic rays? How do you know you found a cosmic ray?
Well, because they are in one image in one position, and in the next image they're not there. Also, they're very hot, they're very bright, and they often come in at sort of an angle so that they kind of shoot across the detector, so sometimes they're elongated.
Okay, they'll look like a streak or something like that had hit
Yeah.
the... Okay. But these don't look like that. They just look like dots.
Yeah, but so there's also another strategy. So we can take multiple exposures to get rid of cosmic rays, but the way we want that we can get rid of bad pixels, if you go to the next slide shows a zoom in of that little purple box on the top of that image, and I'm kind of just showing a zoom in. I've highlighted in green where some bad column and some bad pixels. So we have dead pixels which show up as black, and we have hot pixels which show up as white. And what we do is we actually move the telescope slightly, just by a couple of pixels, so you can actually go through the next 3 slides. And so what you'll notice is that on the detector, those pixels stay in the same place, but the stars, then we move them. So then we can actually combine those 4 exposures and use the 3 good ones to fill in the bad pixel that would be in the position where it was bad in the one image.
Right. So these pixels are either always off or always on all the way, and they don't change position, but you still want to get the star that might be behind one of those, so you move the telescope just a little bit. There's a term for that, isn't it?
It's called dithering.
Dithering, yes.
And the cool thing is, I have one more graphic, and I'll turn it over to everybody else, but if you dither by a fraction of a pixel, you can actually improve the resolution of your image. So if you go to the next, this next slide is all 4 stacked together where the hot pixels have now been replaced. So now this looks pretty ratty because I've zoomed way in, and also because these infrared pixels are very large. But when we use these, so it ends up making these stars look very blocky. But when we do these little small dithers, you can flip to the next image, and the stars become like point sources. They start to become round, and so you're actually able to use software to improve the resolution of the images if you do this special dithering trick.
Okay, so wait, go back to that. Hold, Scott, right there with that one. What is so? That is without. That's the first image, and then by dithering, it gets progressively better with each one.
The previous images.
Is that what we're saying?
The previous one is what the stars look like. They look like little boxes almost.
Yeah, they're very boxy.
There's only, say, 1 pixel or 2 pixels in the light profile of a star. Generally, you want to have multiple pixels so that you can actually sample the light from that star better and measure.
By moving the telescope just a little bit, taking another image and adding it to this one, lining up all the stars, you get this.
Yes.
And then you do it again.
Yeah, so we did it 4 times here, and that we were able to
and
tighten.
each one it got progressively better.
Yes, yes. We're able to basically just improve your resolution of your final image.
Okay. What are the typical exposure time? Well, maybe that's not the way to ask it. Are most people taking images using this camera at about the same exposure, or do they do it at different exposure times? How about you, Jay? Do you know?
Yeah, people can take very short exposures if they have bright objects and you get enough photons or electrons in a single exposure. But if you're looking for very faint objects, then you need to expose for a long time to get enough photons that you believe that the source is there. So people can expose for 1,000 or 1,500 seconds, and that's what, maybe 20 minutes or so.
In one exposure. In one shot.
That's right.
Okay. And I think you know where I'm going to go with this. What are the problems with really long single exposures like that? What happens to the detector when you just leave it open for 20 minutes, let's say?
A couple of things happen. You get a lot of cosmic rays. So cosmic rays are these particles flying through space, and they hit the detector at random places, and that creates a pockmark in your image. And if you leave your detector collecting for too long, your image is going to be full of pockmarks, and you'll have no sense of what the actual sky scene looks like. So you don't want to take exposures that are too long. Also, the longer you leave your detector open, the detector itself glows a little bit, and so it collects its own photons. And that also makes it hard to understand what's coming to you from the sky and what's coming to you from the detector.
Right, that's called dark current, or
That's called dark current.
Yeah, that's just stuff that even if you left, if there was no light, no photons at all hitting the detector, and you turned it on, it's going to just start showing you this snowy pattern. It's a background noise.
That's right. And people, cell phone cameras typically take, tenth of a second exposures or shorter, so they don't need to worry about these kinds of things.
Right. So, what's the advantage? And I think what's the advantage of taking shorter exposures versus long ones? Because if, let's say, okay, what I'm trying to get you to talk about is we're going to add up all of these short exposure images, because the noise, it keeps the noise down and increases the signal.
Yeah, it takes a certain amount of time to read out the image, for one. It takes about 90 seconds to read out a Hubble image. So if you take a whole bunch of 1 second exposures, it's going to take you 91 seconds to collect a 1 second exposure, and that's not very efficient.
Right.
So if you take a 20-minute exposure and then add 90 seconds, most of your time is spent collecting photons, which is what you want to do.
Yes. And another point I wanted to make was whenever you're adding up images like this together, you take, let's say, a 10-minute exposure, whatever you see is going to be very dim, or it's going to be whatever it is, however bright it is. And then you add another 10-minute exposure of the same thing on top of it. Now you've got twice the signal, but the noise didn't go up that much. The noise only went up as the square root of 2. So that's another little thing that astronomers get to enjoy as far as the physics of how all of this works. That really they can take advantage of this. But so there's a tool at the Institute, I believe, that helps astronomers figure this out, right? I think it's called the exposure calculator or something like that. They can tell this application what they want to do, what they want to image, and then along with some other parameters, and it tells them what they should be exposing, right?
That's right.
Yeah. So there is some help available to astronomers for doing this kind of thing. So I just wanted to mention that as well.
So there's one thing, if you take a bunch of exposures, there's one thing that you have to keep in mind is that you'll eventually have to align all of those exposures.
That's right.
So there's only so long you can observe there's a sort of the discrete unit called 1 orbit of Hubble time, which is the time it takes for Hubble to go around the Earth, and that's a 90-minute time frame, and you can observe for about half of that when the Earth is not in your way. The Earth is too bright for us to be having the telescope on, so we can observe for, say, 45 minutes of that. So then what you need to do is then wait 45 minutes, and then you come back and take your next exposure. But you have to reacquire your guide stars, so your pointing is going to be a little bit off. So you actually need to realign all of those frames using sources in your image. So it can actually be a little bit tricky if you have a lot of cosmic rays and not a lot of point sources. It can be a little bit tricky to figure out how to fine-tune that alignment. And one other thing that happens is that as the telescope goes around the Earth, it's going through thermal variations, and so the detector itself they call it breathing, and so there's actually a scale change that the detector itself, or the pixels, are actually changing in scale, so it's kind of shrinking and growing. So we actually correct for all of this in post-processing.
Wow. So, okay, so we've talked about the different kinds of artifacts that are in a raw image. We've seen the big squares from the amplifier differences. We've seen bad pixels. We've seen hot pixels. Those exist in all detectors. And as Dean pointed out, these aren't junk. These are really the best detectors that can be built. These are just part of using CCDs up in space. And every camera has these artifacts. You've got to know what they are. You've got to remove them, and you get the kind of images that Jen showed us. Now, everything that comes back in an image counts on a detector. Those are photons have fallen onto a pixel. They've converted them into so many electrons. Those electrons are counted as a signal. That's the signal. with every, I don't know, Scott, if you could pull that the very last one of Jen's either one of Jen's images that showed just the grayscale. These all they show the points of light or the galaxy, whatever the image was. Here we go. Thank you. So there's no color here. This is all gray. And yet we all go to the Hubble site, and we let these amazing images come out. We see color. Where does that come from? And I'll direct that to you, Jay.
Okay. If Scott, you could put up the slide set that I just recently sent. So let's see. I think the first slide.
Yeah.
Okay. So when Hubble was recently serviced by the space shuttle, they put up a brand new detector that had was called the Wide Field Channel Camera 3, that had a ultraviolet optical channel and an infrared channel. And what Jen just showed us was from the infrared channel. This is from the optical ultraviolet channel. And so when we put this new detector up there, which was state of the art, we wanted to show the public that it was doing great things. And so at the very beginning, people said, well, if you look at this object, you'll get something cool, or that object, you'll get something cool. And we ended up looking at the object that you're seeing on the screen, which is the center of a globular cluster, not because it looked cool, but because it was good for calibration. Because the pictures that you get out, I'm sure people that have watched these before know that instead of having a perfectly square vision of the sky, it's sort of like a fisheye lens a little bit. The stars aren't exactly where they appear on the sky, and we have to understand how the locations of stars have been deformed. And so we took a picture of this cluster because we know exactly where all the stars are in the cluster. And if we take a picture with the camera, then that tells us how to move objects in the camera to properly represent where things are in space.
So I just want to interject that this is like an amazing image. In my career, I have looked at globular clusters, and this is in the center of this globular cluster. And if you tried to take a picture of this cluster from the ground, you would just have a big square of white.
That's exactly right.
These stars, and so we produce these beautiful pictures, but I, who work on clusters, this just warms my heart, because you can stare at this and see the tiniest, faintest, perfect little stars right next to a bright star, and that's the power of the spatial resolution of this telescope. It's just amazing.
Yeah, for years people knew that there were thousands of stars in this little bitty patch of sky, but they could see maybe 2 or 3 bright ones, and then the rest was a mess.
It was just a mess.
So this is amazing. So, but we took this picture to calibrate the fish eye lens nature of the detector, but when we turned it into a color image, people said, this is so beautiful, we have to release this as a demonstration that the telescope is working, because it's just so perfect. And so you see the red stars and the blue stars, and actually this is not photoshopped. So if you go to the next slide, let's see, I think there, was that really the first slide?
That was, let me go back and see if I've got something else here for you.
Okay, that's, so if you have a digital camera or your cell phone, I think most of them, the way they have it is they have a square array of pixels, and they have some that have a red filter, and some that have a green filter, and some that have a blue filter. And when you take a picture, the red pixels only collect red photons, and the green pixels only collect green photons, and then they put it all together into a color picture later.
So Hubble, on the left is what most of our cameras have. They have interspersed color sensitivities all on one detector, but Hubble doesn't do that. Hubble uses the entire detector, and then in front of it they put different filters, and that's what's on the right.
That's right. So instead of getting all 3 colors at the same time, we have to take a red picture, a green picture, and a blue picture, and then we can put it all together with software later. It turns out that the James Webb Space Telescope, which is going up in 2018, will be able to take 2 pictures at the same time of the same piece of sky through 2 different filters. So we'll be able to make our color images instantly.
Woot! Awesome.
So the next slide. I think, okay, so this is the central field that we just showed. The next picture shows what it looks like in blue light. So this is what the blue filter image looks like.
And it's all grayscale. It's
all grayscale, so we get 1 color at a time. But if you look at the red image, which should be next, you'll see that it's almost a completely different star field. The stars that were bright in the blue image, you can hardly see in the red image, and the stars that are bright in the red image you can hardly see in the blue image. So that when you go to the next step, you'll see them all combined together into one image. So the blue.
Okay, now wait a minute here, Jay. I gotta want to talk about this just a little bit.
Sure.
The other images, if you just add them together, they were all grayscale.
That's right.
So if you add them all together, you're still going to get grayscale.
That's right.
What did you do to each one?
Well, we just mapped the
color.
The blue image into blue color and the red image into red color.
So you had a color map. You added a value of colors that said, if in the blue image you see a pixel value that is this high, then assign it this color.
That's right. In the blue scale. That's right.
Right. I bring that up because that's that what we mean by false color, or?
Well, this isn't really false color. This
is
false
real
color comes like with photoshopping type things.
Okay.
This is actually just straight from the detector.
Yeah, let me jump in real quick. For those who do know Photoshop, basically what Jay has done is he put the blue grayscale image in the blue channel in Photoshop, basically, and the red grayscale image in the red channel in Photoshop.
Excellent.
And that's how we make these images.
But we didn't do any artificial contrast or anything like that.
If there's a green channel, you put it in the. Sorry, if there's a green grayscale image, you put that in the green channel in Photoshop. And then when you look at all those channels together, they blend to make a color picture.
Now, the blue light in this image is actually bluer than our eyes could see. We put this detector up there so that it could collect photons that we couldn't get on the ground. So it can actually see bluer things than our eyes can see. And the red filter is actually a bit redder than our eyes can see. So in some sense, this is a false color image because we've mapped the super blue into regular blue and the super red into regular red.
I've actually got a slide that shows that pretty nicely. It's my slide number 22.
Okay. So the point, while Scott's getting that up, the important thing to remember here is nothing is being added to or invented in each of these. These really is how this image looks in the red channel. But sometimes, in order to be able to see it, they may be scaled in a certain way, or maybe somehow enhanced just for the purposes of being able to look nice. There might be some enhancements done, but there's nothing being added to or actually manipulated in any way.
I mean, Hubble is just an extension of our eyes, and so.
Right. Okay. What do we got? What are we looking at here, Jennifer?
Right. So if you kind of look in the, there's a whole range of wavelengths here that are represented, and if you look kind of where the rainbowy part is, that's sort of where your eyes can see. But everything that looks kind of black in the background is what your eye can't see. And so, but we represent things in a way that is, we try to be as scientifically accurate as possible. So if something falls around 4,000 angstroms, we try to make that look blue. And if it falls around, say, 7,000 angstroms, we try to make it look red. And so we'll assign that the color, as Dean said, you assign that as a blue, your blue image. And so, but the thing is, we can't see all light, so we can represent, say, ultraviolet light as blue, and we could represent infrared light as red. So your eye wouldn't actually see it that way, but we try to use physics to determine how to make those assignments so that it actually is physically,
motivated.
Yeah, it's sort of physically, like if our eye could see a further range, then that's what it would look like to us.
And if we don't do that, the thing is that we can look at the black and white images and do scientific analysis, but to appreciate the astrophysics all at once, and by assigning these colors, then we can see things that the telescope can see that we can't see with our eye, and we can understand then the astrophysics that's going on. If we didn't represent, say, if we said, okay, in the red image, we're not going to show anything that is redder than what our eye can see, then that field might not have those bright red objects in them, and we would be losing our understanding of the astrophysics. We wouldn't say, "Oh, wow, there's these big red stars in that cluster. What's that about?"
Yeah,
that's right. When we look up into the sky, we can see some slightly blue and some slightly red stars. Like Sirius is a little bit blue, and Betelgeuse is a little bit red. But we can't see the full extreme of how blue and how red things really are. That's right.
So,
and if you go to the next slide, this shows just sort of how you do that representation. If you take two gray images and you say, now these are both infrared images, but we've assigned one of them is shorter wavelength infrared and one is longer. So this is the Horsehead Nebula, and we So we've called this one, the one on the left, blue, and the one on the right, red. And then when you add them together, is the next slide, that it makes that. It's kind of mind-boggling to me how you could take something that's totally one that's blue and one that's red and then get a colorful image, but that's how it works. I mean, if you take all the colors of the spectrum and add them up, that makes white light.
So Scott, can you back up one again? Those F numbers, those are what? What do they mean?
So if you go back one slide, that shows you the filters. That's the wavelength. So if you look on the right-hand side of the slide, that's infrared. The F110W is about centered on about 1.1 microns. So that's the wavelength of the infrared detector.
How many filters does Hubble have?
How many filters does what have?
How many filters does Hubble have for WIPC3? A bunch?
Probably about 30 or 40.
Yeah, there's a lot.
42 on the visible side, and there's about maybe 10 on the infrared side.
Awesome. So, and again, I think that exposure calculator we talked about earlier helps astronomers figure out what filters they might need to do their science with. So this is how we make the pictures that get released into the public. Dean, can you give us some idea what the difference is between the images that we release to the public that are in these nice TIFFs or JPEGs or whatever, and the kind of images that scientists need to do their work with? There's a difference, right?
Sure. One of the biggest differences is that we use all of the digital information that we can get in the image. So, in an image that a scientist would use, each pixel is represented by up to a 32-bit number. That means there's 32 binary little digits, and that means you can get very high precision. That's more precision than your eyeball could ever perceive. So when we release images to the public, we compress those down to 256 or even 16,000 colors. And that's kind of what Jennifer was saying about the false color. One way to think about the false color is expanding just the visual part that we can see, expand that to include the shortest wavelengths and the longest. And so this happens a lot in digital cameras as well, where people are now using raw images. That's like our FITs. All of the digital information is there. But you know that if you're using Photoshop or you're using Lightroom or Aperture or something like that for your digital photographs, you have to bring them in and convert them from raw to JPEG or something smaller that your eyeballs can see. And so you pick and choose. So there's more information in the digital images that we get down from Hubble than we actually can show on a screen or print in a book. So astronomers need all that information because that gives us the dynamic range that allows us to compare the brightnesses of very bright objects and very faint objects. It gives us the precision, the number of bits, how precise that we can measure something. But when we want to release that to the public, we need to make it sure that the public can understand it. And so we don't need that many bits. We don't need that many colors. So we compress it down. We're not doing anything magic. We're not adding or subtracting anything. We're going to emphasize that over and over again. What we're doing is selecting important pieces of information that convey what we're trying to give. Of course, if you're trying to make a nice, gorgeous picture to hang on the wall, the fact that you've got 32 bits, it doesn't matter if you can only display 16 colors.
That's right. So actually, you bring up a good point. This data that comes down from Hubble is actually pretty big, right?
Very big. I just observed the comet that Rosetta's orbiting yesterday, and each of those files, each of those FITs, we call them FITs. Let's pretend they're called raw files. That's a better way to think of it. If you're thinking about digital SLRs, each of those raw files is 42 megabytes, and I've got 28 of them, and so that's a lot of data.
I'm sorry, how many megabytes?
Each one's 42.
42 megabytes.
And I've got it depends on how many I use, but I got about 28 of those just yesterday.
Well, now I want to talk about Rosetta, but that's a little off topic. So
and that's just one object that Dean
That's just one object and one observation. That's right. That's why.
How many megapixels in each of those images?
It's a good question. These are the 1K arrays. So sorry, 2K arrays. So 2,000 by 2,000.
2,000 by 2,000, and each pixel is 32 bits. So
that's about 4 megapixels.
Yeah. So that's pretty good. That's a pretty large data, and of course, other detectors that'll be launched in the future, JWST among them, will have even more.
Well, actually, that's a good comparison. So I've got a digital SLR that's 8 megapixels, and each of those raw files comes down at around 20 megabytes. And so we've got a 4 megapixel camera that's bringing down 42 megabytes. So you can see the difference in the dynamic and the amount of data that we get off the cameras on the Hubble.
Yeah. And there's other cameras like DCAM, I think, is a 500 megapixel camera. Imagine 500 megapixels times however what is it, 32 bits or maybe it's 64 bits. I'm not sure. You get quite a large. So you go 4 megs or 500 megabytes times the bit depth, and you get quite large images. So, Seth, let me just get to a quick comment here from Seth Duncan on the Q&A app, because he's asking about something we just talked about. I don't want to let too much time go by. He's asking, when you say you're, quote, getting rid of bad pixels and columns, unquote, does this introduce assumed pixels that could possibly provide false data, or is the lost data so small that it's insignificant? In other words, are we putting anything in there to replace the pixels that are bad? And while Jen did comment on that, maybe we should say it again in a different way. We move the camera around a little bit, called dithering, right?
Yeah, so imagine that it's sort of like you have a hole, and so you move the camera around and you fill in that hole with another exposure. So we fill it in with real information.
Right. So we missed it on one exposure because the pixel's bad. There's a star back there, but we didn't get it because the pixel was bad. So you move the camera a little bit, move that bad pixel out of the way, take it again, boom, there's the star. And then when, as Jennifer says, you go to realign all these, you have to realign all this stuff, as many as you take, so it can, there's a balance to be struck, I think. Is that aligning done automatically, Jen?
Yes and no. Some of the data products that come from the telescope are aligned as best as they can based on the information in the image header where the telescope thinks it was pointing. But we do have some inherent uncertainty in where it actually did point, on the order of a few pixels. So things are aligned. Let's say, at the orbital level, if you take a bunch of exposures, say within one orbit, they would be aligned. But if you took a whole bunch of different orbits and you came back and looked at the same galaxy many times, those would not be aligned. And you have to actually use the point sources in your image to compute a solution to align those. And that's actually what I find is one of the trickiest parts of getting the data together, is really making these large stacks. I mean, some of these programs, will have 100 exposures that you're trying to combine, and you have to really do a very good job with the alignment.
I was going to bring up something. We've mostly talked about looking at the objects and how bright they are and what color they are. Jay is actually a master at another aspect, which is dependent on the resolution of Hubble, and that is the position. And if you remember that picture of the globular cluster and where all those objects are, Jay has worked very hard, and you need good calibration in order to do this, but he's worked very hard on the positional accuracy so that you can come back to an object and see what's moved, and maybe you want to talk about that a little bit. So it's not just how bright it is and what color it is, there's other things that we can do with the resolution of Hubble that we can't do with other telescopes.
Yeah, that's right. The image that you showed with all of the stars in the globular cluster, each of those stars is actually moving, because the Earth has to actually be moving around the sun, otherwise it would fall right into the sun. And so all of these stars in the globular cluster can't just be sitting there, but they either have to be moving around each other in some ordered way or just moving around like atoms in a gas, otherwise they would all just fall into each other. And so we've known for years that these stars were moving, but it wasn't until the Hubble went up there that we could actually see it. And this particular star cluster there, we took a picture of where the stars were in 2001. We took another picture in 2006, and we could see how the stars had moved over that period of time. It's hard to see with your eye. There are a few stars that are, say, in front of the cluster that are moving very, very fast. But stars within the cluster move pretty slowly, but a computer can actually measure exactly where they were in 2001 or 2002, and then where they are in 2006, and even 2010, and you can actually watch them moving along a straight line because the stars are moving not fast enough for us to see with our eyes, but the computer can actually measure positions to 1/100th of a pixel. And so we can actually see with the computer exactly how the stars are moving.
Yeah, and that's a science called astrometry.
And if you haven't calibrated your detector very well, then you can't really determine where the exact center of each particular image is. And so that's another reason that calibration is so important, is so that you can find the center of the image and then record it and then come back 5 years, 10 years later and do the same thing. So
yes, that's exactly right. You need to know what motion is related to the detector and not seeing the sky squarely, and what motion is actually true to the stars. So it's actually a very similar kind of calibration to what we're talking about.
Wow, I just realized, gosh, it's 3:45 already, and we're running out of time, and I didn't even get to a lot of topics I want to talk about. I just love talking about this stuff. So, okay, real quick, I want to address the topic of what these kinds of software techniques that we're talking about, the calibration techniques and other software, can do with Hubble data where things are actually wrong. I mean, think something's wrong with the detector. For example, Jay, I worked with you a couple of years ago on some code that you had written in an algorithm you had developed called a charge transfer efficiency correction. I don't want to get into what that was, but what you had done, there was something wrong with the detector, and you had written some code that was able to correct for it. Can you, I don't know if you can describe in big terms what you did with that, but maybe give it a shot, and if it gets too jargony, I'll try and maybe we can translate it a little bit. Okay. But can you give it your best shot on as far as describing to us what that was about?
Sure. So in the very new kinds of detectors, each pixel actually has a separate connection to the readout amplifier, so it can be read out independently. But the old detectors, the CCD detectors that started in 1982 or 1983, are more old-fashioned, and you can't really address each pixel individually. You sort of have this array of pixels in the detector, and each pixel sort of has to be shuffled down to the bottom and then read out.
I have a graphic for that.
This was an older. He's talking about an older camera. It's called the Advanced Camera for Surveys, and this was this was the way it was read out. Okay, go ahead.
Wow, since 1980s,
that's right.
As Jay says, and it's called the bucket brigade technique, where you hand off. You are a pixel, and you hand off your charge to the next one.
That's right.
And hands it off to the amplifier.
And the act of reading it out that way did something to the data, didn't it?
Yeah, it turned out that each pixel wasn't able to transfer its electrons to the next pixel perfectly. So it might have left a drop, if you consider a bucket brigade in water. So it might have left a drop in the pixel rather than transferring it all. So that when we got an image out, it kind of looked a little bit smeared because some of the water didn't make it with the original bucket. It sort of got smeared along the way. It's a pretty regular process how that happened. And so we were able to sort of estimate how much must have been lost in the trail and put that back in the original pixel. It can't be done perfectly.
Love of this is an example of a detector sort of messing up the data a little bit, smearing it out, as Jay said, and the data were still there. You knew how it got smeared,
that's
and
right.
So you could figure out how to unsmear it, and that's what Jay had done very cleverly. And it's not, again, not inventing any technique. It's not throwing away data. It's taking the data that were there, that we knew was there, and we knew how it got smeared, and undoing the problem with the detector.
Yeah, that's slide 26 if you want to show that. It's really, it's pretty cool to see how that gets corrected.
So, 20.
Slide. There it is. Okay,
so Scott's putting it up now.
Yeah.
Okay, there's the smearing. This is from the Advanced Camera from Surveys, and go ahead, Jay. You want to describe this to us?
So the picture on the left shows that the original images, what they look like. And I guess one is a single exposure, and the one on the bottom is a stack, it looks like. And so on the left, you can sort of see the stars have these trails going upwards. And we know actually that those trails aren't part of the stars themselves, but they're an artifact of how the detector is read out. So in the middle,
stars aren't falling.
That's right. They're not falling. They're not crying with their mascara running. This is really something that's happening. Well, when we first saw these images, we sort of cried a little bit because the stars weren't perfect like they had been.
Yeah.
But you can sort of detrail them and get what you see in the middle because it's a very predictable kind of trailing that happens. And then the image on the right shows the difference between where charge was associated with the trail and where it was re-put back into the stars. So dark, of course, means more charge. And so Tony actually helped me make this process faster. As you can imagine, figuring out how 16 million pixels were trailed and related to each other, that's a lot of computation. And Tony helped me put that into GPUs, which are these super high-powered. Well, do you want to explain that, Tony?
Well, those were they were these video cards we got from NVIDIA. Just they were Tesla cards, and they have a set of tools that they've written, software tools that allow you to upload images into those GPU cards and work on each pixel independently. And Jay reworked his algorithm so that it sort of applied the correction in a different way, and we were able to do it in parallel and get it done a little bit faster. So yeah, and that's how I first learned about it, and I wanted to use this as an example, although it's a very difficult thing to understand intuitively what was going on, of another way in which we can calibrate data to get the signal when the instrument is kind of messed up. Now, and I say messed up, I meant, you know, it had a systematic way of reading out that we needed to correct for. Now, we did this also not too long after Hubble was launched. I mean, as everybody knows, when it was first launched, it had spherical aberration, and similar techniques were used. Well, not like this, but corrective techniques were used. Can you talk about that a little bit, Jay?
Sure. It's called deconvolution, and so the original image, instead of having 80% of its light in the central core of a star, it had maybe 20% of its light in the central core and 80% out in a halo. But this halo was very predictable. And so very similar to what we were just looking at, where you have a star and a predictable trail, we had a star and a predictable halo. And so instead of detrailing the trail, we sort of figured out, well, if you have a core here, then a lot of this charge has to do with its halo. And so we can just put that back into the core to get a better sense of what the true scene is that's the sky is delivering to the telescope.
Right, and so we were able to, until it could get repaired, this allowed science to still get done early on in Hubble's life. So I wanted to point that out as well. Let me go to Charles Bell on the Q&A app is asking about the drizzle process. He goes, is that what is referred to as the drizzle process? I think he's talking about the dithering we were talking about. Does anybody want to comment on that real quick, what drizzle is?
I can handle that because that's kind of my expertise.
Okay.
Yeah, there's two aspects of it. Dithering is moving the telescope. So that's a strategy that you use when you're observing. Drizzling is the way that you take the individual exposures and put them together. So the way that you add them up and the way that you can reject those bad pixels, you can reject cosmic rays, you can equalize the sky background, correct for distortion, and align the frames and put them all together or create large mosaics. That's so we have a software that is run in our pipeline called AstroDrizzle, and it uses very accurate calculation of the geometric distortion. It calculates that, and then it puts all of the images together.
Yeah, so it sounds, in addition to being accurate, it sounds delicious. Okay, Dean, we're running out of time. Dean Hines, I need you to comment. So for anybody who watched Space Fan News back in the day, I had Dean on when he first came out with the MyStar game, and the MyStar game was this really fun exercise that you could, well, it's a game you could play, and it really did a good job in teaching a lot about stellar evolution, the life cycles of stars, and things like that. It's still up there. It's still available. If you go to alienearths.org/MyStar, you'll see the main page. It's still up. You can still play it, and people are still actively doing it. But he's got something new to talk about as well. And Dean, go ahead. Talk about it a little bit for us.
All right. So one of the things that happens at the Space Telescope Science Institute is when we observe with the telescope and get grants to make observations, we also sometimes get an education, public outreach component. And so a few years ago, me and a few colleagues at the Space Science Institute, which is another institute I work with, we came up with this idea of MyStar. We've talked to you a little bit about it. Some of you have actually played it. This is a game where you learn about stellar evolution. You pick stars and figure out that their lifetimes depend on mass, and you make solar systems, and you figure out how planets work in solar systems. And this was really designed for small educational activities in the classroom. And we took this to NSF and NASA, and they funded us to make a more expansive system that we could then not only take into classrooms but also deploy it on Facebook and use the power of social media to really expand the educational value. And then also the nice thing about social media is that you play with your friends. If you've ever done Farmville or something like that, and most people have, although Farmville's kind of going away. But the idea is that you play with your friends, you learn, you chat, and the goal is that not only are you having fun and playing a game, but you're also learning real astronomy at the same time. And the success of MyStar, with the success of MyStar, we didn't want to disable that game because we've got several hundred people playing it even now after 4 years. And so instead, what we did is we made a new game, and it's on Facebook in beta testing, and it's called Starkitect. And I'm going to show you a quick screen snap of that.
Right. This is a Facebook game. It's in beta right now.
Yep.
And you'll be able to play it soon. Any idea when?
So we're in beta testing right now. We're in closed beta testing. We're looking at about 6 months probably before we'll open it to open beta testing.
About 6 months. So it's called Starkitect.
Right now, what I'm showing on my screen is MyStar, one of MyStar systems.
Oh.
Called Picus Beta, is something to call it. You can make new systems. You can. I'm out of Starbucks, so I can't make a new system right now.
Okay, so we're running out of time, and I want to be able to let people know about this. How can they find out when it comes out of beta? What are you going to? I mean, we're going to obviously post it on the Hubble Space Telescope Facebook page, but is there a place they can go to get more information?
The first thing you can do is go to the MyStar site. We have a link from the MyStar site that takes you to the beta application.
Okay.
Right now it's not working because we've got it down for some maintenance.
Okay.
You can do that. You can also go to the Starkitect's main site, which is not connected to Facebook, www.starkitect.net/game. And you can actually search for that on Facebook if you want to just search for Starkitect on that.
Awesome. Okay, well, I'll make sure to keep you informed, and we're probably gonna have another hangout with Dean when this goes live anyway. So, but yeah, definitely keep your eyes out for this, folks, because it looks like it's going to be a lot of fun. So, in addition to being a calibration expert, Dean has also been has been making these really great outreach games as well that I think you guys will really like. So, we'll make sure to keep you posted on when that comes out. I want to get to a couple questions here. There was. Let's see, where'd it go? NASA Goddard is asking, what's the image behind J? Was that image behind J part of the Walters Gallery Hubble exhibit? Do you know, Carol, by any chance?
Let me look at it again. Yes, absolutely. Yes, it was. The Antenna Galaxy, and yes, it was.
Okay. And
we've made a couple more of these, I think, and so we do distribute some of them to other libraries and things like that. But yeah, that's one of the ones from the Walters.
Okay, cool. And Aries Keck from Goddard is also she's gotten a question from NASA Hubble and at the Kelvin scale on Twitter. I'm curious to know if the James Webb Telescope will let us image galaxies more efficiently or more clearly. Who wants to take that?
I can take that. This is Dean. The answer is yes. Because it's operating in the infrared instead of the optical, it'll let us see through dust, through obscuring material, and it'll also let us see further back in time. Remember that the universe is expanding, so things get redder as the further away they are because of the universe expansion. So that'll let us observe things that are further away. And also, because it's bigger, we'll have much more sensitivity.
Okay, and as Jay also pointed out, it'll be able to take two images at two wavelengths simultaneously. So that is really cool. So let's see. There was another question from Twitter. Edgar Gonzalez wants to know, how do we know the difference between background noise and what Hubble wants to see? Well, how do we know we're looking at background noise?
I'll try to stab at that quickly. Noise has a different characteristic than real sources. One of the things you can do that Jennifer has already mentioned is if you take an image of the same scene but you move your telescope a little bit, noise will average out and go away. Real sources will persist. Okay, so hey guys, if you guys are using Twitter, use the Hubble Hangout hashtag, and I'll see it too. You don't gotta just go to NASA Goddard there. Although
well,
I've
got some stuff over here, Tony. So here's one from Judy Schmidt, and actually she's sharing an image that she processed from Hubble.
Oh, good.
And
yes,
on Twitter here, you say you find lots of tiny moving things when you process Hubble images, and also miss supernovas. And so if you see here now that Twitter allows for animated GIFs, you can actually see here right in the center.
Awesome, Judy.
Yeah.
Now, this is a good point. We should probably mention this while we're in this hangout. Judy uses the MAST archive to get this data. We should talk about it. How do you get Hubble data? Carol, you want to take that one maybe?
Yes, there are two methods. One is you can go to the Hubble archive, so you can look at Space Telescope Archive or archive@stsci.edu, and use the search form, which is a bit arduous.
Yeah, it's pretty. There it is. It's really pretty, user friendly.
We do have a new portal, which is a little more fun.
Make them work for it.
Yeah, okay. No. If you go to archive.stsci.edu, you can find the portal, which is a little more user-friendly. But there's also something called the Hubble Legacy Archive. And the Hubble Legacy Archive allows you to search by object name or coordinates, and you can look at the data. Usually you get very long lists of data, and pick and choose what you like. And there is an option for looking at where it is on the sky.
Yeah, Scott, can you show that slide? There you go.
Yeah, where it is. So you get this. These are called footprints. So a footprint is where the camera has taken an image, and you can see in this particular galaxy there are many, many footprints. So there's lots of data. And you can also get a preview of a color image. It's pretty crudely processed, but it does try to attempt to do what Jay was talking about, where you assign one filter to blue and one filter to green and one filter to red, and it kind of smushes them together and makes kind of a color image. So you could get an impression of what you might be able to get if you got the data, pulled it into Photoshop, and made a color image yourself. And in fact, we had a couple times we had contests where people went and actually made some really beautiful images from the Hubble archive. We give the scientists, as we talked about in previous Hangouts, we give the scientists a chance to look at their data first and do some science on it, and then the whole archive is open. It's paid for by taxpayer dollars. It belongs to all of you. And you can have both the color images, print them, put them on the wall, or you can try your hand at processing the data.
That's right. All data ultimately make it there that Hubble has ever taken, and with the exception of maybe some time to let astronomers look at it themselves and do their science with it, it'll all get there eventually. So that's great. So that's how you get it yourself, and people like Judy are already doing some great stuff with this stuff. So awesome work, Judy. Thanks for sharing that with us. Alessandra Rosati on Twitter. Yay! She comments she's geeking out about what the Hubble telescope filters can do to get us seeing the cosmos in beautiful ways. That's right. Hopefully now you have more background on how this is done and has been done throughout the years. And like I said before, folks, if you're young, getting started out, even if you're not, you're a good programmer, this is where if you want to work in astronomy, this is a growing industry, I'm telling you. So let's see here. What kinds? Oh, man, we got a lot of questions on Q&A app. Thank you guys for talking about this. Nerdcraft Kirkster. What kinds of gas clouds can be seen through an infrared camera telescope? So, what can infrared do for us that optical doesn't do? What's so great about infrared? Jay, come on. I know you can do that one.
I think Dean is actually more of an infrared expert.
Dean, okay. All right. Go ahead, Dean.
Yeah. So. It turns out that stars form in big dusty gas balls, and it's hard to see them. So if you want to understand how a star is forming, either in our own galaxy inside a molecular cloud with lots of dust, or even in other galaxies like Andromeda or the small and large Magellanic clouds, you really need to go to the infrared to see what's happening. The other thing that we do with infrared that's very relevant nowadays is look for planets forming around stars. Planets, again, form, even though you can see the star, there's usually a circumstellar dust disk around these stars, and you can't actually see the planet form if you're looking in visible light. But if you look in the infrared, you can actually see these warm balls of gas and dust that are forming planets. And so that's two of the reasons. And then the other one is the early universe was full of star formation with brand new galaxies forming, and that's a very dusty process too. So if you want to understand how galaxies were assembled and formed, you need to go to the infrared. And finally, a lot of diagnostics that we're interested in to understand if life exists around other stars, for example, a lot of the signals that let us at least understand if there's something that's interesting there, like carbon dioxide gas, ice, and CO ice, and even water ice. A lot of those things are only easily found in the infrared, so that's why we're going to the infrared.
And I always say the future of astronomy is in the infrared. That's just so much there that we haven't seen yet. So thank you for that question. Nerdcraft, that was really good. I know we're going a little bit late, guys, but I just want to try and get some more in. Here's one from Adam Synergy, also on the Q&A app. How was the Hubble palette developed? Was it trial and error to find some combination of colors that is aesthetically pleasing? That might be more a question for Zolt LeVay, but I don't know. Was there any special thought given to these color palettes? Like Dean mentioned, we put, you could imagine each of these filters as going into a separate channel. You could have the red filter being the red channel, a green filter being a green channel, and on and on. Was any other thought given to the kinds of palettes we apply to these images?
Well, I can address that.
Okay, great.
In general, so Hubble is a wonderful telescope, and it makes some of the most beautiful astronomical images, but visualization of astronomy data is an old art. So it didn't just come, we didn't make it up for our telescope. People have been doing, in fact, there's a gentleman named Dave Malin who has done unbelievably beautiful astro images with the telescope in Australia. So people have been processing astronomical images for a long time and have developed techniques depending on the filter set, and Jen showed the filter set that their observatory uses. Typically what we try to do is, as you said, blue, green, red, because that's what people are used to, that's what we see, but then we also extend that to way blue and the infrared, just to give people the sense of what we call the heat scale or the thermometer scale. But there are other circumstances where we have to use different mapping of the digital data into a color to represent the astrophysics. And those cases are cases where we are looking at nebula that are emitting at very particular energies. And so we want to demonstrate, for example, carbon is emitting at a particular energy, and we want to show that as some color like blue, and oxygen maybe is yellow, or hydrogen is red. And we want to show if we use the regular thermal scale, we might not be able to distinguish things as well. We try to stick with that scale. You know, blue is the higher energy, red is the lower energy, just like we do for stars, but we sometimes need to mix and match. The more complicated cases where we have these emitting from certain kinds of elements, plus we have stars. So then we have to adjust the color palette so that you can appreciate the field of stars as well as the nebula. And that's where it goes away from science and becomes a way of stimulating your visual impression of the astrophysics. And that's the point. Not just for beauty, we love how beautiful they are, but we do it to represent the physical phenomenon which we are capturing with the detectors.
Yeah, wonderful.
It's almost
Thank you.
kind of like a map. You can have a map where you have multiple layers on the map, and then you can use that to see, oh, these two things look like they're associated physically. So it helps astronomers understand the physics of what's going on by mapping those all together and making the colors look very different. Then you can kind of in your own mind help understand what's going on in the image.
And so all kinds of visualization techniques are used to think of weather maps and things like that. They map different colors into different things. Usually for temperature, it's a heat map, but for storms, they might use something else. So it's that idea. How can you convey a physical phenomenon to a viewer?
Okay, so let me. I'm gonna before we're over time. We're 10 minutes later than we usually go. This has been a lot of information. I've had a great time. A lot of comments, but let me just check with Scott real quick. Anything I'm missing, Scott, that I should probably bring up now, or?
The only other thing here is from, let me pull this back up, from Kimberly Archon, is she put a post up on Twitter. I put it into the event page, but she is actually from Chandra, and there's a HuffPo article that she and,
I saw that, yes.
and Megan Watsky wrote over here on HuffPo about coloring the universe, and so how these images are processed, especially using Chandra, but all the other space observatories. So that link is
good point. Good point. Because when you have X-ray, we can't see those at all. So they have to make a decision about that. And when we combine X-ray and Hubble, like Chandra and Hubble, or Hubble and Spitzer, or Chandra, Hubble and Spitzer, or ground-based, or whatever, then you have to start really making some decisions about how best to convey the data.
Right. And so that link is up over on Twitter, and it's on the event page, and I'll put it onto YouTube when we're done.
Awesome. Okay. Well, folks, I'm going to have to let these guys go. They only agreed for an hour, and here I am keeping them here. I want to thank you, Dean, Jay, and Jennifer. Thank you so much for this. This has been a great hangout. I believe we should probably do another one. Dean, look out for here. You're going to be hearing from us on doing when the Facebook game comes out back, so I hope you'll be back for that too.
Sounds good. I will.
Yeah, thank you all. I want to remind you that we are taking a 2-week break. We won't be back until September 10th, where we're going to be back with a bang, literally. We're going to be talking about supernovae and the research and discoveries made with supernova using the Hubble Space Telescope. And we hope you will make it, or it's a slightly different time. I think we're doing it Wednesday, September 10th, right, Carol? Does that sound right to you?
That's correct, yeah.
So be aware that we'll be starting a little bit early because we want to. It's not our usual time, so I just wanted to point that out. And I'm going to leave you guys with a little from Hugo Burnham, who has left on the Q&A app. To paraphrase Tony's famous catchphrase, it's not mine. It was invented by someone else, but I use it all the time. Jack Horkheimer. Once you are properly calibrated, got the right color filters in place, set your bit depth, shuffled your pixels into the right order, unsmeared your image, and wiped away the drizzle, keep looking up. Thank you all for watching. And on behalf of Carol Christian and Scott Lewis, I want to thank you again. See you guys in 2 weeks.
2 weeks.
Thank you. Thanks, everybody. Bye.
On that hashtag since we had Libby Doodle on there. So please come back.
Hey, Libby Doodle's awesome. And
yeah, she was great.
Yeah.
So please tweet at us using that hashtag as well. As always, there's the comments on YouTube and Google Plus event page as well. So get ready. Tell us your thoughts and your comments and your questions, and we'll get to them later on in the Hangout. So today, we are talking about the Hubble Space Telescope and getting what we do with the data from it. Now, astronomy and cosmology, probably more than any other science, really benefits from the laws of electromagnetic radiation. The things that the laws of physics that govern how a photon gets to us, its wavelength, its place in the universe, all of these things allow astronomers to learn about places we could never hope to get to. They're just too far away. The outer, distant reaches of the universe are accessible to us because of the photons that travel to Earth from all of these different places. So what's really cool about this is that astronomers have developed all kinds of techniques for gathering these photons. And we're talking about some pretty faint photons, folks. I mean, some of them literally arrive in just a few batches of photons at once. And some of them travel for billions of years. And they finally get to the Hubble Space Telescope. Their feeble signal hits the detector. And depending on what the detector is made of, whether it's silicon or mercad telluride, whatever it happens to be, those photons will somehow create a little, using the photoelectric effect, a little electron. And those electrons spread throughout, and we do all kinds of wonderful things with them. We're going to talk about that today. But like I said, astronomy and cosmology, gets to benefit, I think, more than most other sciences about this. And it's also a topic, but none of it actually can get done without calibrating the images that we take, because as these photons are falling onto the detectors, they're building up signal, and images are being created, and they're being transmitted down to the Earth, and we're doing all kinds of stuff with it. And that's the topic of this hangout. What are we doing? What is the stuff that we're doing to these images once the raw data have been taken, and to do not only make the pretty pictures that come out of it, but also to do meaningful science? How do we know about things like the distant universe, the distant galaxies, what the exoplanet atmospheres are made of, whether there's even an exoplanet there or not? So these are things that we're going to talk about today. It's a subject near and dear to my heart because up until the time I started working at the Institute, this was my career. I worked as a person who wrote software to calibrate astronomical images. In fact, I called myself an astronomical programmer, and that had less to do with how good of a programmer I thought I was as to the type of programming I did. So, and for the young people out here watching this hangout, if you're thinking about a career, this is a growth industry. Writing code that calibrates astronomical images is in high demand right now. In fact, if you watched our Pan-STARRS hangout with Robert Lupton, he came on and basically begged for programmers to go work for the LSST. So this is a growth industry. So if you're young, just starting out in your career, it's something to think about. And today we're going to talk about some of the steps to do that with. And with me today are 3 astronomers that all work at the Space Telescope Science Institute. I have, and I'm going to go from my left to right, Dr. Dean Hines. He's an astronomer here at the Institute, Dr. Jay Anderson, and Dr. Jennifer Mack. Welcome, guys. You guys are all experts on calibrating data for the Hubble Space Telescope. And I think last week we had a workshop on Hubble calibration. Now, Hubble's been around for almost 25 years. How come we're still meeting to talk about calibration? Jennifer, can you help us with that? Tell us a little bit about the workshop.
Okay, well, so I think really the main point of this was to tell people how to get the most out of their data. So they get calibrated data products that are in our archive, and what we're trying to let them know is what are possibly some limitations in those data products, how well calibrated are the different instruments, and what can they do at their home institution to maybe reprocess those and make them even better. And so when we talk about calibration, you had talked about, we measure some electron. So that's actually what we get. We'll get a raw image with some number of counts, and then the goal is of calibration is to translate that into some sort of an absolute brightness. So imagine, you had
has 4 amplifiers.
So far as the WIF-C3 does, the ACS does. I'm not sure about the others.
And they're all at different levels, it looks like, because
most detectors on telescopes have at least 4 detectors. I mean, amplifiers, if not more. Okay. They're not always blocked like this, but they typically have more than one, so you can read out the problem is to be able to read out the charge, measure the electrons quickly, and the more amplifiers, the faster you can go.
And you can't make 4 amplifiers that are exactly the same. Is that why they look different? Is that the reason for them being different? They're so distinct.
That's correct.
Okay. So, and I'm also seeing some little stripes here, and what do those stripes do to those big thick stripes that are like several dozen pixels wide? Do you see those?
I don't know exactly what that is. I mean, but this is all just signal from the detector itself.
Okay, so maybe read out as it was read out or something like that. These artifacts.
So let me just say, okay, sort of like your cell phone, we have these little tiny solid-state detector elements that are in an array, and that's what you're seeing, 4 arrays. And when the charge is accumulated, it's sent to a bit bucket, essentially, and the amplifier then sends it to the rest of the electronics. And so sometimes you have variations between each one of the little pixels, but you can also have variations that are along bands, and it's just how the electronics get read out, and then that's kind of noise. And so what Jennifer's describing is Well, that's not an astronomical image yet, because a lot of the stuff that's coming out is not from the galaxy, it's from the detector. So we want to get rid of that stuff so we can say what's left is exactly from the galaxy and not from the detector. Because even if you try these kind of exposures at night with your cell phone and your friend's cell phone, you'll get different kinds of things that may have those kind of features. It's just that we use our phones when there's a lot of light and we don't see all that stuff. But it's a similar technology.
Excellent, thank you, Kelly. So the takeaway here, what I wanted to show was that the camera, the nature of the camera itself, introduces all these things that have to be dealt with. Now these
60-watt bulb, and you were standing and you put it a mile away, and you could measure. Oh, I got 10 electrons from that, and then you can tie that. You can tie that to an absolute system. So what we do is we look at stars that we know how bright they are on in an absolute sense, and then that's how we can tie everything to sort of an absolute brightness.
Okay, so do astronomers meet every year? Do we have this workshop every year to talk about these problems and issues with calibrating, or is this just a once in a while we do this?
Every few years we get
together. Every few years?
For this, yes.
Okay. Well, great. So let's go back.
2005, 2009, and 2010, 2014.
And I imagine there's somebody has figured out some cool way of doing something different, and maybe it's a good way to learn about these kinds of things with Hubble data. Now you brought this up, so let's talk about this for a second. Hubble is sitting up in space. We all know that. It's looking all over the universe. It looks at everything from planets to exoplanets, to distant stars, distant galaxies. And the photons come in. They hit our detectors. They get transmitted down to Earth via the system of satellites called tease. We get the data at the Institute. What does it look like when we first get it, when we first see it?
So I have a slide there that...
Okay, Scott, can you put that up for us?
It's so pretty.
Okay, so this is an example of a raw image from the Wide Field Camera 3 infrared detector. So you can see there's a galaxy. You can see a lot of other structure in there. For one, you can see the 4 different amplifiers. You can see some kind of striping. So a lot of what you're seeing here is signal from the detector electronics. When you're looking at in the infrared, it sees heat. So it sees heat from the instrument itself, and that actually kind of blinds you a little bit. So what we do is first we remove that signal, and you can flip to the next image, and then you can...
Okay, wait, before you go though, go back one more time. Those 4 big squares, what are they again?
Those are 4 different amplifiers. This
so this is a raw image from the Wide Field Camera 3. It's in the infrared range because that's the kind of camera it is. And these 4 big squares they're 4 amplifiers. Is this typical of all cameras, or is it just the WFC 3 that? Hello everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really interesting hangout plan for you today. We're going to delve deep into some of the technical details of using the Hubble Space Telescope, and specifically how we calibrate the data that come off of the telescope. So with me, as they are each week, are my cohorts and colleagues, Dr. Carol Christian, she's the Hubble Space Telescope outreach astronomer, and Scott Lewis from KnowTheCosmos.com, the Virtual Star Party, and the Internet in general. So welcome, guys.
I will be your guide.
I will be. So welcome, and they are here to help me with this hangout. But before I get started, I want to make a quick announcement that we're going to be getting started this week, and you'll see some more social media postings on it from our channels next week as well. NASA is trying to make trying to get a panel together for South by Southwest. Now that's that's usually held in March, and that is because the Hubble 25th anniversary will be so close by. It'll have a very heavy Hubble component, but to get the panel, I guess South by Southwest is having a voting process. I don't know if they always did this, but this year it's a voting thing, and I've put the link to how to vote in the details of the Google Plus Hangout. I've also been retweeting people who pointed to the links on our Twitter channel as well, Jason Calilbrating, Amber Strawn, those guys. So if you have a moment, please go and vote for the Hubble panel at South by Southwest so that we can get that rolling. We'd very much like to be there and show you some of the latest things going on with Hubble at South by Southwest. So I wanted to make that announcement. As far as this Hangout goes, before I get to the introductions of my guests, let me just say, interact with us, folks. And by now, if you've watched with our Hubble Hangouts for any length of time, you know the drill. The Q&A app is my favorite. It's the easiest. It's very cool, very easy, very handsome. I like it. So use the Q&A app. You can also comment on Twitter. Hubble Hangout is the hashtag, and we'll see that as well. And come on, folks, tweet. I mean, we haven't had any Twitter activity